So today I want to talk to you about malware detection and what have been the trends in malware detection, both in the academic community and in industry. And I want in particular to talk about how we came to use machine learning for malware detection. As you may be aware, machine learning has had a big revolution in the past few years. It's very prevalent in a multitude of domains. There have been great progress in image recognition, face recognition. These technologies are in our phones, but also both text translation and topic identification techniques, or even text generation. We've seen many recent breakthroughs even in the past few weeks. However, it's not as much widespread in the security industry, and this has been researched in this academic community also for about, I would argue, more or less more than 10 years. So the question is why isn't, especially in the context of malware detection, why isn't machine learning as widespread in industry? The key point is that security is an adversarial context by nature. Attackers will try to evade detection, so they will try to evade the machine learning system. If we want to represent it in a bit more formal terms, let's say that the benign applications follow a certain distribution, and if the attackers develop something malicious, it follows another distribution. And let's say that antivirus companies can identify a certain threshold to distinguish between benign and malicious. The problem comes when attackers want to mimic benign behavior, so that it creates a confusion between what is benign and what is malicious, and it is not able to distinguish them anymore. But this is not a problem just necessarily in security and in malware detection. It can be in any domain, like even computer vision, and it depends more about threat model and what you're looking at, and that's why also both academia and industry have been working into understanding properties of robustness of machine learning in a plethora of domains. But today I want to talk more more specifically about malware detection, and I want to start with I want to actually use as a running example more of the mobile applications, because malware can take different forms, and in general, malware is any malicious software that does something to compromise the confidentiality, integrity, availability, or privacy of a user or a system. And while malware can take many forms, it can be a Windows PE, a JavaScript plugin, it can be like a DLL, but it's easy to think of it as the mobile application is self-contained, and it's easier to think about it as a case study. So let's say that we're an antivirus company and we want to evaluate whether a certain application is benign or malicious. So what is the first thing that we do? Well, first of all, we do some static and dynamic analysis. Static and dynamic analysis derive from compiler theory even. It's they're very basic computer science knowledge, and for example, dynamic analysis is based on principle of debugging and inserting breakpoints in code, so most of you may be familiar with it. But the intuition is to get a representation of the behavior of an application. Static analysis evaluates an application without executing it, so it's a static evaluation of the code. And this is often, there are a variety of techniques, often from the field of program analysis, that try to evaluate the code and possible branches or state representations, and there are behaviors for it.
This is kind of like, what might this do?
Yes, exactly. But of course there are different levels of precision that you may achieve. Static analysis can also be very lightweight. It can be just even counting the API calls that are present in a certain piece of software. Of course, that is not a very relevant, it does not describe any complex behavior per se, so it's a very lightweight static analysis, but the coexistence of certain APIs can still reveal that something malicious, that it may identify something that is common also in other malicious applications. And dynamic analysis, on the other hand, is kind of to complement it. It's more like an actual execution of the application. So it executes the app, and generates an execution trace. And as I told you, it's based off debugging principle. It's like inserting a lot of breakpoints and monitoring the system calls and taking the arguments. And again, you can have different levels of precision also here. Of course, the more precision you want to have, the more expensive the analysis becomes. In dynamic analysis, you get the behavior of an actual execution of the application. So it has the benefit over static analysis of observing real behavior. Think about even a social network app, and maybe there are parts of the social network app that are even never reached, right? Or are not very commonly used. Of course, a problem that is typical of dynamic analysis is like stimulation, right? It's like you need to simulate what the users would do, like to provide a proper coverage of the application. In a sense, dynamic analysis provides an under approximation of an application behavior because it's like just an actual execution, whereas static analysis provides an over approximation. Maybe there are some areas of code that will never or hardly be reached in an actual execution, but still maybe you give importance to them. Indeed, one strategy that attackers use to complicate this type of to complicate detection that they're doing something malicious is to add a lot of junk code that is maybe then taken into account into static analysis, and then you end up with very complex abstract syntax trees or control flow graphs, and it makes it very complex then to distinguish what is actually going on and what the application is doing.
So they might kind of put a load of libraries in for, I don't know, images or something, which it never uses, but
Yes.
they get added up and checked, and this is just something to do with images, right?
Exactly. Yes, it's exactly like you say. It's they may insert a lot of junk, and actually one of the most common techniques that are used nowadays is like called piggybacking, which you take, for example, an app, like a game app, and then which like 99% of the app is maybe benign, and then you inject something malicious in it. So it makes it even harder to analyze and identify the malicious part that is triggered. So static and dynamic analysis will be the basis of malware detection, regardless of whether we use machine learning or something else. But what is the something else that has been historically used by antivirus systems is like signature-based detection. Let me just write SBD. Typically, antivirus companies will have a database of signatures that are like, they can be as simple as sequence of bytes, like that they have been found in malware. And if a signature match is found, then the application is detected as malware. Otherwise, it's just assume that it's a benign application. But signatures can be also more complicated. They can be, I mean, you can think of them as regular expression. They can even be like, there are typically languages to like explain or express signatures in more complex signatures. Like they can also be behavioral signatures about whether an app is doing X and doing Y and doing Z. Then we have seen it in the past, it's a malicious app. The problem with signatures-based detection, although this is still used, the problem is that it's time-consuming. Of course, attackers, in a sense, work 24/7 to develop new strategies to evade detection. So it becomes more, it takes time for defenders to come up with the proper signatures that also have the good amount of false positives and false negatives, right? You don't want to overlap with benign software, detect benign software by accident. And database of signatures then become more and more complex to maintain because they're error prone. Like imagine like if you, I mean, anyone that has been worked with regular expression, it may be the same. Like if you start having just a set of keyword compositions that can be used in a form, let's say, then the more keyword you start allowing, I mean, of course, let's say that you want to express words as regular expressions, right? The more rules you start adding to this form, the more likely then you will either exclude something that was allowed before or include something that should not be allowed. So where does this take us? It takes us like to then also using machine learning as another way of detecting malware. It's still built off of static and dynamic analysis, so like it inherits strengths and weaknesses of these approaches. Let's say that you could also especially with the rise of deep learning and the many successes of deep learning, you can even ideally throw an app inside the machine learning algorithm or like a deep learning algorithm so that it then learns. Deep learning is representation learning, so it can learn automatically a representation of the application and its behaviors. But I think that the problem there is that most of the neural networks that we have nowadays are for other tasks, like for voice recognition, text understanding, or text translation, or image recognition. They're not suitable to identify program behavior, so it will just identify spurious correlation and treat the app as an image, for example. So I think that it's very prevalent yet to just perform static and dynamic analysis and define with human expertise signatures that can express behaviors. Back to the point, like why isn't machine learning as popular in industry for malware detection as it is for other tasks? And one big aspect is that since security is adversarial, as I pointed out before, malware evolves quickly over time. So like, let's say an underlying assumption of machine learning is that training and testing roughly follow the same distribution. Of course, machine learning is about learning from data. So actually, there's also a way of saying in the machine learning community that it's like garbage in, garbage out. Like if you have poor data representation in the training set, whatever the machine learning algorithm learns will also be useless for the task that you want to solve. In this case, it's not necessarily a garbage problem, but it's more like maybe you train from data from a set of benign and malicious applications from 2019, but then attackers develop new strategies, and now those apps are not representative anymore of the current threat scenario. So malware evolution is really, it's often referred as concept drift as well, or like distribution shift in technical terms. And it's a real challenge for this domain, but it's not also, let's say, we should not like surrender. There are techniques even for the machine learning community that can be adopted in these cases, like such as active learning or line learning, or another intuition is like classification with rejection. It's another approach. Like the intuition is that you may, for example, discard and quarantine decisions that have uncertain probabilities, like in which case, like if we want to distinguish between goodware and malware, if the malware detection system tells that it is a malware with 55% probability, well, it most likely is. I mean, it's very uncertain about it. It's like it's a very, very minor likelihood that it's like a malware, so you may decide to quarantine and threshold it, right? So let's say, and that actually, this is what the security academic community has been working on as well. It's like trying to understand ways to adapt and to this drift, and like understand how to maintain the machine learning models accurate over time. People may think that, and also when I started working in this field, I also thought that, okay, there is malware and there is goodware, they're clearly separate, right? But sometimes it's not as clear. You could debate that without context, certain applications, such as, I don't know, even an email application or a social network application could be just identified as malware, right? So context is important, but yes, also the different families. Originally, the families were like very, very distinct. You had ransomware that encrypts your data and asks for ransom. You had like spyware that wanted just to steal your data secretly. You had, apps that maybe steal credentials, specifically just credentials for bank accounts. But nowadays, also the categories have become also more merged. It's more typical that a malware does multiple malicious behaviors at a time because they want to achieve different objectives. And also over time, the same malware family will change slightly objectives. And this is part of the reason that complicates the whole detection, yes. We talk about the malware evolution over time. Another thing that is very important to consider is that we cannot so the attackers are not blind. If we start using machine learning for detecting malware, then they can also take advantage of the fact that we use machine learning to further evade our system. And in a sense, as we add machine learning as defenders, we increase the attack surface for our system, because then the attackers can target this. Many people may have heard about adversarial machine learning, and this is what this is about. It's become very popular in the image domain, where you have this image of a panda, you add a little bit of visually imperceptible pixel perturbation, which is carefully crafted, and suddenly the panda, by all machine learning system, is detected as another animal. In the malware detection domain, the principle remains the same, but it's a little bit more complicated. You cannot just, as in the image domain, randomly add bytes to the software. It will just not run. And even something simple that has made the news, such as adding a little bit of bytes at the end of a file, it's not sufficient, because even just compilers will remove junk code or unreachable code, or sometimes it's called also dead code. It depends on the type of technique. But if the code is clearly not reachable, then it will be discarded by the analysis system, so the attack will be ineffective. Attackers may have objectives such as preserving the malicious functionality or making it plausible, so that, for example, it's not a torch app that weighs like 3 gigabytes. Part of the reason in which there was, I think, in the early 2010s, industry tried to use machine learning as it is, and then nothing was working, nothing was explainable, it wasn't reliable, so there was a moment in which it was completely discarded. But in that scenario, I think that the problem was that we should avoid having a false sense of security. One thing that was very typical, and still is, in the machine learning community is to do k-fold cross-validation. So you divide your data sets into folds, in this example like 6 folds, then you use 1 fold for testing and the rest for training, and then you rotate. And the principle is that you want to avoid picking a lucky slice, right? You want to see whether your approach generalizes to different conditions. The problem in security is that if you do this, you are, in a sense, integrating future knowledge in the training set. You're disregarding the temporal separation that needs to be present between training and testing set, right? If you have 3 new malware families here that appeared just last year, by rotating you will integrate them in the training set, whereas if they come later, they should be temporally separate also in your evaluation. In a sense, we should become more aware of, in a sense, the do's and don'ts of machine learning for computer security and malware detection, and use these techniques more appropriately.
As I understand it, when a machine learning system is very good at choosing stuff it's been, or identifying stuff it's been trained on, it's called overfitting, isn't it?
Yes.
And is that the big problem here? Because it's seeing things that are new, it's seeing things it hasn't found yet in the wild after it's been trained that's the problem. Is there any point in doing this, I suppose, is what I'm thinking, if that's the big problem, it's identifying new stuff?
Yeah, so I would argue that I think identifying new stuff maybe has a natural language meaning and a more technical terms meaning. I mean, there are actually, when you say identifying new stuff, people would expect that it is able to identify everything possible. But at the same time, when I talk about this, you can see it as something similar to overfitting. In a sense, it's related. I wouldn't say it's exactly the same thing. It is learning a lot from the training data, and people then may say, but then it's completely unable to learn new things. I think the truth is somewhere in the middle, in the sense that the objective is to have a good static and dynamic analysis that give you also the right level of behavior representation. So it's all about, as in many things in computer science, it's a lot about abstract representations. So that with machine learning, you can automatically learn what are some key elements that represent actually malicious behaviors. This will allow then to identify new variants also at test time, because it will anyway recognize the underlying patterns. So the thing is that in many cases, attackers just do the same thing in a different way. And I think this is the key point. And I think if machine learning can help us understanding and scaling to detecting the underlying strategies of attackers, then it can generalize in a sense to identify new threats. The problem currently is that with the representations that we have, they're able to just do the same thing in such a different way that the machine learning will not be able to detect it. So this is actually the key problem here. The holy grail of malware detection is having the right level of abstract representation to identify malicious behaviors.
Which will change this number and hopefully increase it until that is the category that is seen in the image and not the giraffe. So this number will go down and this one will go up, but only changes 1 pixel.
Let's just write a very silly little Python program. So I can write this function. Let me make a little bit of bigger font size for you.